safer, more connected, more accessible, and more prosperous. And we prove every day that with enough support, enough intellectual stimulation, and enough collaboration, nothing is impossible. Our purpose and our goal is to fuel our members' imaginations, to support their ambitions, and to inspire the rest of the world to do what has always come naturally to us: to dream.
Ladies and gentlemen, please welcome AIAA Executive Director Sandy Magnus.
Well, good morning, everyone. Happy Monday, and welcome to Propulsion Energy 2014. Are you guys all awake and ready to go? Oh, you can do better than that. Come on, let's hear you. Good morning. All right, that's excellent. Welcome to Cleveland. We're really excited about this week. Of course, this is a great place to have our Propulsion and Energy Conference. Ohio, as many of you know, is a home to a lot of aerospace here. We have 120 aerospace firms based in the state today, doing over $7 billion in business. And so Ohio's been on the leading edge of aerospace for a long time. There are 11,800 Ohioans employed by 62 firms. So the state is actually the nation's second biggest contributor in these areas. So this is a good home for us. And of course, Glenn Research Center is here, a home of one of NASA's centers. I did some graduate work here, so it almost feels like a second home for me to be back, although it's much more fun to be here in the summer and the wintertime, I will say. This is going to be a really great week. We have the theme for this year is leveraging technology synergies to realize the promise of interdependent systems. And we're all here from industry, government, academia. There's going to be some great conversations this week about the state of the propulsion and energy sector of aerospace. And I know that you are going to enjoy yourselves and learn a little bit and meet old friends. And I would encourage you to, make sure you meet at least 5 or 10 new people. The power of bringing our community together in forums like this is so that we get a chance to meet each other, we get a chance to network, we get a chance to find out what's going on across the industry and learn a little bit. And so I'm looking forward to popping in and out of sessions and doing that myself. And I hope I get a chance to meet some of you that I haven't met yet. We have a really strong program, and the reason why we have a really strong program is there's a really dedicated group of people who got together to organize the forum. So on behalf of everyone here and AIAA, I'd like to thank all of the members who served on the Executive Steering Committee, the Forum Organizing Committee, and the Technical Program Committee. So those of you who served on one of those 3 committees in the audience, could you stand up, please, so we can thank you with a round of applause? Very good. Thank you very much. They've been working for about a year to bring the program together, and I think they've done an excellent job. Also, of course, we couldn't put on our forums without our sponsors, so let me take a moment to thank our sponsors for Propulsion and Energy 2014, GE, NASA, Lockheed Martin Corporation, our additional sponsors, Dunmore Corporation, IEEE, and COSI, Jacobs, Ohio Aerospace Institute, Sierra Lobo, Southwest Research Institute, and United Launch Alliance, and finally our media sponsor, Space News. So we thank you all for your support as well, and I look forward to meeting some of the representatives of those companies this week. Also, for those of you who do tweeting, we have a Twitter contest this week, and we've got some great prizes, and you'll see that information in the program. And even if you don't personally like to tweet, there'll be a lot of great comments going out on the Twitter feed at #PropEnergy. And it's been really fun as we've started doing this at the conferences just to look at people's comments as they've come out of a great session and talk about what just happened. And it's kind of a way to stay in touch with what's going on with the rest of the forum, even though you can't go to all of the sessions because there's just so many great conversations going on. It's hard to keep up with them on your own. And just a little bit of admin. We're going to be doing Q&A, of course, at all the sessions this week, and we have microphones stationed in the aisles for that, and that will make sure everybody can hear your questions. And some of our sessions are being live streamed, and that will allow people who are watching online to be able to see them, hear the questions as well during those interactive sessions. So right now, I'd like to introduce Mike Heil, who's the President and Chief Executive Officer of the Ohio Aerospace Institute, and he's the General Chair of the AIAA Propulsion and Energy Forum for 2014. We have all of the biographies of all the speakers posted on the website, so I'm not going to go through his biography here, so I encourage you to go check that out on the website. But Mike, if you would like to come to the podium and take over, which means you need to come out from behind the curtain. There you go. Excellent. Thank you.
Thanks, Sandy. On behalf of the Executive Steering Committee, I'd like to welcome all of you to AIAA Propulsion and Energy 2014 and remark that this marks the 50th anniversary of the Joint Propulsion Conference. And there is no more appropriate place to come to celebrate that 50th anniversary than Ohio and Cleveland, Ohio, because of course Ohio is the birthplace of aviation, starting with the Wright brothers who figured out and invented controlled powered flight. And of course that lightweight gasoline engine, the propulsion part of that flight, I think was one of the key enabling technologies for that. But we're also the home of such icons as Neil Armstrong, John Glenn, premier propulsion and energy research laboratories at NASA Glenn Research Center and Air Force Research Lab at Wright-Patterson, great propulsion and energy companies and world-class research universities. So I'd like to thank the AIAA staff, all the sponsors and planners who helped put this together, also our co-sponsors and professional societies that we're working with, in particular IEEE and INCOSI, who are going to bring the systems perspective, who are helping us with Energy Check 2014 here at this conference, and then Energy Check 2015 will also be in Cleveland. But also, most of all, I want to thank you, the participants of this conference. Thank you for attending. We've got a great program for you today. You'll have an opportunity to make connections. You'll have an opportunity to learn from world-class experts and gain knowledge. And I just ask that you use this experience from this forum to go build the future of propulsion and energy. So I think this forum will be very, very helpful for you. Today we're going to be having an energy focus at this forum. Tomorrow, a propulsion focus today. Tomorrow the focus will be on energy, and then on Wednesday the focus will be on advanced manufacturing. So we're going to start off with a great opening plenary panel looking to the future. And they're going to look 10 to 50 years into the future, looking at systems architectures that are safe, clean, and economical. We have a tremendous panel assembled for you. The panel moderator I'd like to introduce at this point is the Center Director of the NASA Glenn Research Center, Mr. Jim Free. He's had a stellar career within NASA at several centers. I'm not going to give him a long introduction. You can read it on the website. But please give a warm welcome to our panel moderator for the opening plenary panel, Mr. Jim Free.
Thanks, Mike. Thank you. Well, good morning. Thank you very much, Mike. It is a great honor for me to be here today. I want to welcome all of you here today. You've heard a little bit about the week preview from Sandy and Mike, and I'm sure that our discussion over the next hour with our guests will be great. I do have to say that my first AIAA Propulsion Conference, when I actually did real work, was in Nashville at the Grand Ole Opry Conference Center there. And I still remember those days of walking in and seeing a group like this and meeting folks and how incredibly impressive it was. I'd like to thank AIAA, Dr. Sandy Magnus for this honor, the organizing committee for putting this together. It is a tremendous opportunity for the city of Cleveland to host a group like you. Propulsion and energy, as you've heard, are core to what Ohio does, and the facilities here in Cleveland at NASA Glenn, which I'll share a little bit about later, are a great example of what can be accomplished with innovative thinking. I'd like to start today by introducing our panelists. Our first panelist, Dr. Narendra Joshi, is truly filling in at the last moment. Dr. James Mahan from GE was the unfortunate recipient of weather cancellations last night. I'm sure many of you had some delays at least. Graciously standing in for him, Dr. Joshi is the Advanced Technology Leader, Chief Scientist at GE Global Research, where he manages a portfolio of technology programs directed towards aircraft propulsion applications. He received a PhD in mechanical engineering from the University of New York at Stony Brook in 1984, and his undergraduate degree in mechanical engineering from IIT in Bombay in 1979. Our next panelist, Dr. Rick Parker from Rolls-Royce, is the Director of Research and Technology. He was appointed Director of Research Technology, Rolls-Royce Group in January 2001, and is responsible for the direction and coordination of all R&T programs at Rolls-Royce. He earned his BS in physics at Imperial College London in 1975 and an MBA with distinction at Loughborough University in 1992. Our last panelist, Dr. Eric Bachelet, is the Executive Vice President, Research and Technology for the Safran Group. He joined SNECMA in 1974, and prior to his current position, he was appointed president of CFM International, a tremendous, I think, innovative way to build engines in 2005. He holds degrees from the Paris School of Mines, 1968, and Case Western right here in Cleveland in 1973. It is a pleasure to be here with these impressive gentlemen, and I thank you very much for making a time to participate in this panel. The theme of this panel is Art of the Possible in Propulsion and Energy Technology over the next 10 to 50 years, and we were just having some interesting conversations before this about what that means. And of course, our ability to see in the future is not so great, but what we can see is the ability to think of innovative ways to do things, to really dream, and as we put it in NASA Glenn, dream big. What I'd like to do first is share this quote with you. Anything one man can imagine, other men can make real. That comes from Around the World in 80 Days by Jules Verne in 1873. A bit of innovative thinking even then. I think it would more appropriately read, anything anyone can imagine, others can make real. That's one simple truth that I believe has really stood the test of time. As you see and hear the technologies this entire week, whether it's propulsion, energy, additive manufacturing. You'll hear some of those ideas this morning from GE, from Rolls-Royce, from Safran, and from NASA. And you'll hear about that technology that we need to enable those ideas to become reality. We're going to have our panelists either step up to the podium or from their seats, whatever they're comfortable with. And at the conclusion, I'll share NASA's perspective, and then hopefully we'll have some time for questions. So first, I'd like to welcome Dr. Joshi to the podium.
Thanks, Jim. Thanks, Jim. When I look at the big crowd here and I think of what has happened yesterday, James Mann couldn't make it here because of the challenges for travel. And so, from the standpoint, the weather was interesting, but even more interesting was the challenges that he faced in getting here. So in 2064, I hope we'll be better able to forecast weather and be able to deal with that better. The art of what is possible is a very, very interesting and challenging topic, because you go back to the work of Jules Verne and others. The masters of science fiction were able to dream and imagine new technology. For example, Jules Verne himself was the person who imagined that cities would be lit with electricity when people were playing or doing experiments with frogs' legs and batteries. So it is possible for us to think of what is going to happen next, but you need to be a master of science fiction. I'm reminded of the series on Discovery Channel from several years ago, when they actually had this series on Masters of Science Fiction. And now the big challenge for us is to think about how are we going to improve from where we are today. In the last 50 years, the fuel burn per passenger seat mile has come down by about 82%. A very significant improvement if you look at where we are now. But in the next so many years, because of the massive pressures that we have on fuel burn and the number of people who are flying, the way we can do that is to try to get even better. 82% fuel burn relative to 1960, we'll be looking at that and seeing how we can get that the next step. So starting with thermodynamics, perhaps, the way to look at something like this would be to do an exergy analysis for transporting people and say, where are we making best use of our capabilities? So you got the airframers and you got the propulsion systems. So if you look at both of those and in total, look at how we can change that, the big question is going to be how can we imagine what is going to be the next what should I say, innovation. In terms of innovation, what has happened generally is the thing that gets funded gets developed. So if you can imagine something and get it funded and create local value, then you will find a pathway to the areas where you think you want to be. So if you look at it from that perspective, aircrafts were funded by companies, technologies were developed by people like NASA, the DOD, and others. And when the two came together, there was a massive investment in infrastructure. So if you go back and look at the amount of infrastructure that has been built over the last 50 years or so, you have perhaps 20,000 airplanes flying around. Then you will have the airport infrastructure, the fueling infrastructure. So if you start adding up all of those, you'll come up to numbers which will exceed somewhere between $20 and $50 trillion. Now, there is a lot of momentum when you have that much invested to think about new technologies which is going to displace the investment of $20 to $50 trillion. So it is not an easy challenge to dream of next generation of technologies. We know a lot of things that are in the pipeline today. We have better propulsors, so we'll be looking at things like open rotors. You have distributed propulsion. So you can think of many, many propulsion-related items. Then you look at gas turbine engines, which is what we have today. You can think of making better gas turbine engines. You can go to the next step and see that you can get lower cost fuels. Then you can also look at saying that, can I get better, more efficient conversion of fuel energy to electricity, which can drive my propellers. So the next place may be you come up with something like solid oxide fuel cells. But all of that can happen because we have imagined it within the next 20 to 30 years. What happened beyond that is a big question. Perhaps there is personalization of the aerospace industry. If you look at healthcare, they have moved from the direction of having one medicine that fits all. The new research is coming back and telling us about personalization of medicine. In the same way, perhaps you could imagine personalization of the aviation industry, where you would be able to go from one point to another point and not have to get to an airport, get checked in, fly on an aircraft with hundreds of people with you, and get someplace else where you need it to be. So that is one of the things that I think we can look at as one of the potential trends going out in 50 years. So you'll see technology moving components to the super system, such as the fueling infrastructure has become a super system, the airports have become a super system, and at the other end, you go to the micro scale, where you do the personalization of the industry. So with that, the only thing that comes to my mind is for this kind of innovation, we have to dream differently and look at things beyond what we already have on paper, because that's what I think will happen about 50 years from now. Thank you.
Very nice. Thank you, Dr. Bush. Next, I'd like to welcome Dr. Rick Parker to the podium.
Oops. No, I don't think that's my presentation. I can always give Eric's for him, but it might make life more interesting. Shall I skip through to mine, or do you want to take Eric next? That looks like it's got my name on at least, so good start. Okay, good morning, everybody. We're asked to gaze into the future this morning. And I've chosen just one aspect of our industry to look at where large civil aircraft propulsion is going over the next 50 years. I'm reminded of the words of the physicist and mathematician Niels Bohr, who said that prediction is very difficult, especially if it's about the future. And with that word of caution, I'll start. The best place to start in looking out to the future, I want to investigate this area of where evolution is going to give up and revolution is going to take over. So evolution says start from today, and I think we're in an amazing position today. We have come a long way in our industry. We have one of the world's most advanced passenger aircraft ever flying in the Boeing 787. Rolls-Royce's Trent 1000 engine was the lead engine on that. And it's a more electric, nearly all electric aircraft and a nearly all composite aircraft. So a great step forward for our industry. And the next step forward, heading off into the future, is this aircraft from Airbus, the Airbus A350, which will enter service with Qatar later this year. And again, Rolls-Royce is the sole engine this time on that aircraft. And for a very brief period of time, we can lay claim to the accolade, the world's most efficient aero gas turbine. But I'm sure my colleagues in GE will be working hard to knock us off that podium any day now. So that's the starting point. That Trent XWB engine is the latest in our family of three-shaft engines. The three-shaft architecture is something Rolls-Royce has pioneered and driven through. And it delivers about a 50-to-1 pressure ratio. So just show you a little animation. You can see there the two cores, the high pressure spool in pink, the low pressure spool in yellow. And the work split's about equal between those two. So 5 years out, we're going to radically change that core, go to a very different work split, offload the intermediate pressure spool, and put a very lightweight low pressure system on that. So a composite titanium fan and a composite casing, low weight LP turbine. Even at 11-to-1 pressure ratio there, with the three-shaft architecture, we haven't yet reached that tipping point where the weight and complexity of a gearbox outweighs the weight and complexity of lower speed, lower efficiency components. And that's primarily because we don't have a big low speed booster on the fan shaft. We have an intermediate pressure compressor that finds its own speed. So that's the first step in this evolution. That takes us out to about 2020, so 5 years into the future. If we look beyond that, then fan size is going to keep growing. That's almost inevitable. We're going to get out to bypass ratios around 13-to-1 and above that. And when you get to that point, even we in Rolls-Royce eventually have to give way to the gearbox. So this is our XWB again. And as we move to the next generation, we keep basically the same core. We put a gearbox now between that intermediate pressure compressor and this even bigger fan, continue using the composite and titanium technology. And that takes us out into this region 2025 and beyond. Now a very high-speed LP turbine, high efficiency, or IP turbine as we're calling it, fused with the original intermediate pressure turbine. So that evolution takes us out, as I say, 2025, and pressure ratio or bypass ratios up to around 15-to-1. Significant further increases in efficiency. All of these are datum from the first of our Trent series of engines back in the 1990s, 20% and 25% more efficient. That means less CO2, better for the planet. And you can see the building blocks of technology that go in there. So one of the things we always say in Rolls-Royce is invent once and use many times. So having got a key technology, build on it, improve it, but keep it running forward into the next generation. If we want to look out beyond that to 2030, and I'm sure Eric may say something about this as well, then bypass ratios beyond about 15 or 16-to-1, the whole drag of the nacelle, the weight of the nacelle starts to dominate the design of the aircraft. and the performance of the aircraft. So you really got to get rid of that nacelle, and that means going back to propellers, or what we call these days open rotors. The testing we and Safran have done around open rotors say you can deal, at least at today's legislative levels, with the noise from an open rotor. You can beat today's Chapter 4 noise requirements. You have a margin even to Chapter 14. But the whole issue is predicated on where future noise regulation goes. But as you can see, you get a very impressive reduction in fuel burn, and again, cleaning up. So that's really where the evolutionary story starts to give out. The next step, we in the engine industry don't have a free hand. It's where's the aircraft manufacturer going to go? What's their dream for the future? Well, Rolls-Royce was very proud to be the partner of all three aircraft manufacturers in this recent NASA program. So we worked with Lockheed Martin on their back box wing construction, and we looked at how our UltraFan would work on that. We worked with Northrop Grumman on an ultra-quiet aircraft with our Advanced 3 engine in that, and we worked with Boeing on an open rotor-powered blended wing body with the engines set up high above the aircraft to benefit maximum from the noise shielding at the ground. And again, you can see all of those meeting impressive targets, but you can also see there's no free lunch. All of these things, fuel burn, NOx, emissions, and noise, are fighting against each other. So no one configuration got a tick in the box for every one of the NASA targets. And the NASA targets are very similar to our ACARI European targets. So there's a real fight out there to get there. But then when we come to further evolution, I would pick on two things that are going to characterize that. One is distributed propulsion. So we've gone from 4 engines to 3 engines to 2 engines. It'd be a little dangerous to go to 1 engine. In fact, as most fighter pilots will tell you, the advantage of a 2-engine aircraft is that when one of them fails, you know you've got just enough power to get to the scene of the crash. But so distributed propulsion, and the second key trend, and you'll see plenty more about that in the next 3 days, is more electric technology. So electric drive taking over from this, from conventional direct drive. The first one of these couple of concept aircraft we've been looking at, this is an ultra-slender wing, 8 open rotors driven electrically, powered by 2 gas turbines mounted on the wing there. So may get us outside today's wing box configurations for airports, so they may have to broaden a few airports. And taking advantage of the blown wing to get extra lift or enough lift from this very slender wing design. And that's been a study we've been doing with Cranfield University recently. Another UK study done jointly with Airbus and Cranfield University is really the hybrid car of the air. This is the Toyota Prius of the air, has 6 superconducting electric motors driving 6 fans and 1 gas turbine providing the power for the 6 motors and a large battery providing additional power. But again, just like the Prius, when you're coming and coasting into to land, those fans are acting as generators and generating electricity. When you're taking off, you have the battery power and the gas turbine power getting you into the air. And that's what it looks like on the inside. You see the 6 fans there. Single gas turbine at the back providing thrust, but also providing the electricity and the battery. Now, none of that technology is light enough today to get into the air, but with superconducting developments, with battery developments, certainly in this period we're asked to gaze out in the future to out to 2050 or even 2064, then I think this sort of concept will be possible, and that's where I want to leave it today. Thank you very much for your attention.
Thank you, Rick. Now I'd like to welcome Dr. Eric Bachelet to the podium.
Good morning, ladies and gentlemen. I will share with you Safran's perspective on the future of propulsion energy and how we prepare ourselves for it. To do so, I will follow the thread which was laid out by the organizers of the conference. First of all, what are the big mega trends or high-level drivers for future evolution? They are very simple. We are in a world in motion, more open, more interrelated, with a growing population, and the demand for mobility will continue to grow faster than GDP in the next few decades. This backdrop means that in the medium to long term, we'll face an ever-increasing pressure on energy, resource, economy, and sustainability will be the key requirements for all issues around propulsion and energy. From this standpoint, for the last 50 years, we have made tremendous progress within what we can refer to as the current paradigm. This paradigm has been simply described as 2 plus wing, plus 2 or 4 turbofans hanging below wing for the fixed wing aircraft, and turboshaft plus mechanical transmission for the rotary wing. The turbines provide about all the energy required by the mission, whether propulsive or non-propulsive. Jet A is the fuel. Airframe and engine are mildly integrated. Within this paradigm, we have made tremendous progress, gaining about 1% of fuel burn per year and reducing emissions very significantly on CO2, NOx, noise, etc. These reductions have warranted the social acceptability of the growth of our industry without limitation. And it could be noted that airplanes that were designed in the mid-60s, like the 737, or A320 in the mid-70s, are still flying today, will be built with improvements, spiraling improvements with new engines, new systems, and so on, until about 2030, and we probably fly until 2050, 2055. However, there is a general consensus that we are reaching the limit of this paradigm. If we take as a reference the engines that are currently flying today, such as the CFM56-5 or -7B, flying on A320s or or Boeing 737, will introduce a new generation of engines in 2016 or 2017, the LEAP engine for Safran and GE for CFM, and they will bring about a 15% improvement in fuel burn. In the following year, around 2020, we'll have made further improvements of those engines, gained another probably 3 to 5%, bringing altogether the improvement to 20%. In parallel, we are developing advanced projects and will be testing the following generations of engines with ultra-high bypass ratio. For instance, a ducted fan with bypass ratios of about 16, or open rotor to gain possibly a further 10 to 15% with the engine. But we believe that this is probably the limit of the current paradigm, as we are entering, as evidenced on the chart, limits on temperature of material, on pressure that are available due to the reduction in size in compressors. We are reaching cycle efficiencies with the Brayton cycle. We are also facing other type of inefficiencies, some related to the emissions. We ask contradictory requirements from our engines. For instance, we have high thrust at takeoff and very high efficiency at cruise for the airliners. For the helicopters, most of the mission is done at cruise, and yet we can only use our engines at 50% of max power because we must have an instant surge capacity to face any issues. Efficiencies also come, and it is well recognized from the fact that on the airplane, in terms of energy, we are using various forms of energy, and this puts limits on the capability to optimize the energy as a system. So what can we do to rethink the paradigm? To do so, we can address 3 sets of consideration. The first one is, how can we use the turbo machine at its optimum and enhance the propulsive energy of the propulsion system? We can play with several things. First of all, primary sources. Can we go beyond the Brayton cycle to non-Brayton cycles? Can we use fuel cells? And how far and when we'll be able to use them? What will be the technological limits? The second thing is propulsive architecture. How far can we go with the gas turbine? I think I outlined this to some extent. We can play with hybridation. What does the injection of electrical energy, how can it assist to the turbo machine, and how can we improve the overall cycle of the propulsion system? And then we can play on the architecture, the aircraft architecture. We are on tube and wings. We'll see more integration already with higher bypass ratios. Can we go to buried engine? Can we even go further to distributed propulsion? And of course, the trends there are for the more electric aircraft, more integration, possibility distributed propulsion. We will have to, of course, always keep in mind safety and redundancy. And we certainly will face certification issues. The third consideration is energy harvesting. How far can we go in energy harvesting? Potential and kinetic energy, for instance, and thermal energy as well. One question asked by the organizer is, how are we addressing these trends? The first thing is in terms of product developments. Safran has been developing equipment addressing the more electrical aircraft. For instance, we proposed the first ETRAS, electrical thrust reverser actuation systems for the A380, the first EBAC, electrical braking actuation for the 787, and we are developing an electrical green taxing system which allows planes to be on ground without manned propulsion. And if you look at it, it's really shifting the burden of propelling the airplane on the ground from the main engine to the APU, and perhaps tomorrow to a more complex hybrid systems. The second way we are addressing these trends is through organization. At the beginning of this year, we have creating within the company a business unit that's called Labinal Power System that encompasses all aspects of the electric aircraft. It's a 12,000 people, about a $3 billion business unit, and it covers everything from electric architecture to electric generation, to wiring, to power electronics, and so on. And we did so to be able to have a complete integrated view covering all aspects of systems architecture, of the electric system architecture. The third big way we are addressing these trends is through R&T. We are developing systems engineering again, and trying to develop a global competence in energy system management through modeling and being able to define optimums to steer our products development to better answer the requirements, the future requirements of the airframers. The third one, in R&T also, a very important thing that we are trying to do is to have an interdisciplinary approach or cross-disciplinary approach to the energy problem by making work together, specialists in thermal propulsion, I would say, turbofans, turbo engines, and so on, and electric and electronic specialists, as well as propulsion and non-propulsion specialists, because innovations is at the boundary of all these fields. And finally, we work on all technologies related to energy storage and hybridation. One question again asked by the organizer was, what kind of eye do you keep on disruptive technologies? We are watching closely what's going on with the automotive industry. The automotive industry is facing the same societal challenges as we do. And they have been very innovative developing hybridation, electrical cars, when nobody believed in it 15 years ago. They develop interesting concepts, start and stops, for instance, and a lot of technologies in power electronics, energy storage, and they are even introducing the first hydrogen distribution stations in the US and in Europe. So this is really something we keep an eye on. The second set of technologies is fuel cells and hydrogen generation. Fuel cells are far from being efficient for use on airplanes today, but with improvement, they can probably provide the flexibility we need to redefine the architecture and the boundaries between a propulsive and a non-propulsive energy. The third type of technologies that we are looking at is energy storage and supraconductivity. Again, we are very far from making it available for airplanes, but this needs to be looked at. And finally, something that must be considered is for the primary sources of energy is beyond the fossil fuel, a Jet 1 source, renewable jet hydrocarbons. We believe that we are at the beginning of the technologies to produce renewable hydrocarbons, both from the agricultural point and then the transformation point, and they will have to play a role if we want to keep this industry sustainable and socially accepted. Finally, to conclude, what are the trends for 2064? Well, it's very difficult to predict. I first believe that we believe that the gas turbine is not dead, but as a primary power production, but it's very likely to be complemented with a fuel cell. We'll probably still use hydrocarbons, but with significant renewable sources. The integration between the propulsion and airframe, which will much more advanced, whether it's ultra high bypass ratio engines, will possibly have distributed propulsion. Hydraulics will have been turned to electrical on all non-propulsive functions, simply because to really get the weight benefit of the electrical system, you have to eliminate hydraulics. And possibly, but this seems to be a bit far out, supraconductive electric networks might be used for machines of very high power. The challenges are power density of electric technologies. They are cryogenic technology safety, if we think about them. Regulations, adapting the regulations will be hard. And finally, inserting of those technologies in a current aviation system, in vintage aircraft fleets and ground operation networks will be a challenge. And to conclude, we believe that more than ever, the dialogue between the airframer and the equipment suppliers, whether engines or else, will be more crucial than it has been. Thank you.
Very good.
Thank you very much,
Surprising
Eric.
agreement. People will think we talk to each other.
We didn't.
Okay, I'd like to take a few minutes to share with you the NASA perspective, and I do want to recognize the current and former NASA employees that are here. I'm going to speak to you today as a NASA employee, but about NASA Glenn, but I'm very proud of the work that goes on at NASA in propulsion and energy, and as I mentioned, I'll talk about the NASA Glenn story today. You heard a little bit of the history about NASA Glenn. We are 2 campuses here in Cleveland, so it's only the first few charts that are commercial, I promise, for NASA Glenn. We'll move past it quickly. 2 campuses here, one right next to the airport where most of you came in, and the other about 50 miles from here. Both very unique facilities in the people. That's always first in my mind, the people that do the work, and the facilities that we have in which we do the work, whether it's a laboratory or test tunnels. Highly educated workforce, and has been making a difference here in this community for 70 plus years now. Very well established from an awards perspective, I will say, and I'm sorry to the other NASA employees now, but NASA Glenn, 116 R&D 100 awards, more than all the rest of NASA combined. We just won 2 more 2 weeks ago. Very proud of those awards and the folks that have won them. You've heard tremendous discussion from our 3 other panelists about different aspects of the propulsion and energy field. Where we start at NASA Glenn with our 6 core competencies and power being one of them, there's a number of technologies that are used in any application relative to power systems. Sometimes it's the conversion mechanisms that you use that differ, but either way you have to generate the power, you have to store the power, you have to transmit the power, and you have to have loads on the other end. And that's how we look at NASA. And the technologies that support all those scale up and down in most cases and are applicable across all of them. Oops, excuse me. So first, the three portions of the triangle that NASA Glenn works in: space, power, and propulsion. We'll talk some more in depth about that, of what we're doing now in solar electric propulsion. Obviously in the air, you've heard from our 3 other panelists, NASA Glenn has a significant role in that. And again, those technologies support those too. And then how do we bring that down to earth? NASA Glenn's mission statement is about driving research and technology and advancing systems in the air, in space, and on the ground. That's where we see all 3 of those connected, and where hopefully many of you will make those connections this week. Let me first talk about space, solar electric propulsion. We're currently working on a mission to fly the highest power solar electric propulsion system flown to date. 30 kilowatts is where we're starting. We're looking at 5 kilowatts being flown today. Many of you know that much better than I do. We're looking at 30. We're going to 300 kilowatts. How do we do that safely, efficiently, and affordably in the environment that we're in today? Well, here's those elements. That common chart I started with, here's the elements we use to do that. Advanced solar arrays. We're developing right now 25 kilowatts and greater. Obviously, we need to transmit it. We have that load at the other end of these 12 to 15 kilowatt engines, and we need to be able to store it. The next leg, the air side. The evolution, which you've heard from our 3 other speakers about going to a more electric and maybe all electric aircraft one day. We're starting with that at NASA, our partners at NASA Langley, on the smaller aircraft, the personal aircraft, eventually with our goal out at the commercial end, commercial airliners, some of which you heard about earlier with the turboelectric and distributed propulsion. That distributed propulsion is going to need different elements in addition to the power system. It's going to need materials work. You heard some of that from 2 of our speakers today already. How we distribute that propulsion, how we distribute the power, how we generate the electricity and power to use in flight is critical. Going back to those common elements that NASA Glenn works on. Now we're pulling on some other sets. We're also pulling on some we didn't on the space side. But we're leveraging what's done in space, we're leveraging what's done in air, and letting those 2 play off of each other to advance the technology. When we look at on the ground, I mentioned our mission statement about improving life on Earth. The energy trends that we have, I think we're all familiar with these. What's happening with fossil fuel where we're getting that power from, how we're generating it, how we're working on efficiency. We talked about profit margins on airlines, a 5% profit margin. If we can help in the domestic use on the ground by improving efficiency by 1%, 2%, think of the savings that impact the economy there. We believe that NASA has, across NASA, not just NASA Glenn, can contribute to all of those trends. So the third element of that triangle, I'm going quickly because hearing from you is important too, so I want to save some time for questions. The third element of that triangle is how do we do things to take those technologies that have been developed for space, take those technologies that have been developed for the air, and now apply them on the ground. Look at those trends to help us figure out where to go, and look at the technologies that NASA has broadly that can affect it. I will mention one here is a thermoacoustic system that we licensed to a couple of investors that's going to really transform home energy. Actually, the first market for it's the UK. The product was announced about a year ago. It's going to be in its final form this fall. Something we're very much proud of, where NASA technology has come back to help really close that loop from a NASA perspective on the investment that the taxpayers have made in us. So that third element of the triangle now uses, again, some common sets of all those technologies that we need. We've leveraged our dollars to help other applications, but we've also made a difference right here on the ground. Some specific advances, I talked about the solar arrays that we're working on. Solar cell technology, 4-junction solar cells, highly efficient, lightweight solar array technology to be used in space. NASA develops things for our missions, but we're really a marginal buyer. It's the commercial industry that uses these technologies, all of you sitting in this room. Our work in wind turbines started in the 70s. I see a couple folks out here who played a role in that. How can we help with wind turbine technology today, taking our expertise in aircraft engines? Our expertise in icing is another application that we can use. Energy storage batteries, our work to improve work on space batteries, ports over into work on aircraft, the lithium-ion technology, other chemistries. We have agreements with a national lab, the Joint Center for Energy Storage Research, thinking of those crazy chemistries to improve battery storage and capacitors as well. Fuel cells, the jump that Dr. Bachelet talked about from 0.5 kilowatt per kilogram to 10 kilowatts per kilogram. That's a big jump. NASA Glenn specifically is right at the center of that with our work in flywheels, our work in fuel cells. How can we improve those technologies for our space missions, our aircraft missions, and move on from there? Power management. Some of you know in this room, the power management system and the distribution system on Space Station was designed right here at NASA Glenn before being passed over to the contractor. We're looking at intelligent power systems, smart grid. We're doing a great amount of work in smart grid work right now. And then the integration and the flexibility, Stirling cycle, Brayton cycle, really world-renowned experts right here at NASA. How we integrate those renewable sources into a grid. A lot of analysis going on in that area right now. Alternative fuels research. NASA Glenn's more about the characterization of those fuels at this time, but still things like green propellants is work we're focused on as well. So moving forward, those technologies that we need to advance power, propulsion, and energy really exist today in some form. It might be TRL-1, it might be, as I always put it, that thing I saw work in a cartoon once, right? But they do exist. They are highly advanced. It's how we leverage them from here, how we can improve on them. And they certainly, as I've talked, those 3 legs have multiple applications. Our mission statement again at NASA Glenn, driving that research and technology. GRC, big government, big in acronyms. We're always going to have that R in our acronym. So it's our research and technology that differentiate us. And we're really leveraging those technologies in propulsion today to address those future challenges. So we're going to open up to questions, but I'd like to finish with one thought. I think Mike said this is the 50th version of this conference, and the theme of this panel is the future in 10 to 50 years. So 50 years ago at the first conference, did those folks think about the 50 years ahead of them, and what were their thoughts at that time? We're at that next point, and a big milestone, and we're looking 50 years out. And I think it speaks to Sandy and Mike and the organizing committee to put this first in the week. Think about that future in 50 years as you're meeting those 5 people Sandy asked you to meet today. You 6 people are going to be the difference in what's decided in 50 years. And we have to have the courage to think differently, and we have to have the courage to pursue things. I think we're seeing that in a lot of different areas of the world. Our panelists here, their companies, other government organizations across the world, and specifically NASA. So thank you very much. I guess what I'd like to do now is open the floor up to questions. I can't tell if folks are leaving. Is this something I said? There's got to be one question out there. Yes, sir. Could you go to the mic, please? Oh, it's right in the middle there. I'm sorry.
Thank you. Joe Doychek, Office of Naval Research, former NASA Glenn employee. Nothing was mentioned about supersonic travel. Do the panelists envision supersonic transports, commercial supersonic transports in the 10 to 50 year range?
I didn't get the question.
Supersonic transports, that wasn't mentioned. What are the thoughts from the panelists on supersonic? Go ahead, Rick.
Yeah, supersonic transport has never totally disappeared off the scene. I think we're all, there's been a lot of work done on supersonic business jets, for instance, and I think my personal view is that'll be the first form of supersonic transport. It's taken a bit of a backseat for 2 reasons. One is it's never going to be as good for the planet in terms of CO2 and everything else per passenger, per kilometer as conventional flight. So there's a sort of guilt factor that's come in to prevent people pushing it quite as hard and quite as fast as we were 10 years ago. The second most critical thing, and this is where NASA has a crucial role to play, is it only becomes commercially viable if you can fly over land supersonically. Now, there's been some great work done, notably by Gulfstream, but also by others, in diffusing the sonic boom at the ground down to less than half a PSI. So you really wouldn't disturb people. You certainly wouldn't be knocking the glass out of their greenhouses. But we got together a group of people, I think it was about 8 years ago now, called the Super 10 Consortium, which with NASA was going to do a flight demonstrator to prove that that was true, that you could fly over ground supersonically without unduly disturbing people or scaring the horses. And I really look to NASA to take a lead again in getting that demonstrator done, because I think it would advance the whole industry. From there, we may get back to supersonic transport. I mean, we and our colleagues in SNECMA were very proud to power the 12 Concorde that were out there for over 30 years. So that was, in a way, our industry's taken a step back since that period.
Thanks, Joe. And NASA's reformulating its aeronautics strategy, and one of the early demonstrators is a low boom demonstrator, and have already been doing work in the desert with the F-18 to start that project. Oh, are you allowed to ask a question, Sandy? I guess if anybody can ask a question, you can.
Yeah, I always have lots of questions. It's a blessing and a curse for the world around me. It was very interesting listening to your conversations about what the technologies are that we could evolve and then revolutionary go to. I'm wondering if you could make a comment on what your thoughts, what that means to the workforce. You know, we're already in aerospace a very multidisciplinary field, and as we move forward, do you anticipate the way engineers are trained need to be changing, or how we how we interface with different disciplines changing, because you have to get even more and more multidisciplinary when you start talking about distributed systems and how you systems engineer all that together. So I wonder if you could talk a little bit about the implications on workforce training, or if you see any or not.
And you reformulate?
Yeah.
Sure. So the workforce, with these
Skills.
transformative technologies, how do we change the workforce either in how they're trained or the interfaces between systems?
Say that one.
Yeah, I think the workforce that is coming out of universities now is very different than it was 20 and 30 years ago. So the workforce is very capable. You see tremendous skills in the new people that are coming out of universities. And to your point, Sandy, we will need to get better training, especially cross-training between different disciplines. Mechanical engineering and electrical engineering, for example. These two disciplines are taught differently in universities, and electives are different. So at some point in time, we'll need people to cross-train as you get greater integration of electric and mechanical propulsion systems.
Do you want to say anything, Eric?
No. If you look at aerospace, engineers always have a relatively multidisciplinary approach, and I think this will be more and more emphasized. And if you look at the workforce, the blue collars, I think, or assembly people and so on, they have to accompany on their technical skills the complexity, the development of the complexity of our systems. If we want to attract good people, we have really to provide them with 21st century jobs, if I may say, And this means training, again, skills, more skills, more variety of skills, understanding of what they do, and so on.
I think if the West is going to maintain its competitive edge, looking at some of the technologies we've shown you today, one of the critical points in there is electrical engineering. And we're not talking about electronics, we're talking about things that make a big spark. And it's true that in both America and in Europe, the number of graduates we're creating in those areas continues to decline. Whereas if you look at China, India, even Singapore graduates nearly as many electrical engineers each year in this tiny island as the whole of the United Kingdom. We have a major competitive threat if we don't refocus our skills in those areas going forward.
Thanks, Rick. Let's see. Okay, well, thank you all for your attendance today. I appreciate the panelists' time, and hope you all have a really great week.
Good. Good start.